You're all full of energy. Good. End of the day. Okay, so what we're going to see today is this evening. So what did we see this morning? This morning we worked our way up to more or less a justification of the Fourier coefficient formulae. Just these three formulae here. Okay. This is what our typical Fourier series looks like. This equation here, this expression for a function is an infinite combination of sines and cosines. The infinite combination is determined by the values of these parameters, or coefficients is a better word, but the coefficients in this linear combination. And those coefficients are given by these formulae here. They're integrals of the function f, which is multiplied by something. What the function f is multiplied by is the corresponding basis function. Constant function 1, or the cosine function, or the sine function. Okay. So this is very much a continuous version of what you know from, say, 2- and 3-dimensional vector spaces. That a vector can be written as a linear combination of your nice basis vectors. What are the coefficients in that linear combination? Well, when you're using the nicest of all bases, standard basis, which is an orthonormal basis, all the vectors are orthogonal to one another, perpendicular, they're all of length 1, then your vector, the coefficients in the linear combination of the basis vectors is equal to the dot product between the vector and the relevant basis vector. And these are what you think of, they're the continuous versions of the dot product of your vector that you're looking at f with the relevant basis vector. Because it's continuous, we're in this continuous setting of an infinite dimensional vector space of functions, it's an integral of the product of our function f with one of the basis functions. So what we're going to do now is start looking at some genuine concrete examples. Specific functions f and discovering, obtaining their Fourier series. Okay? So we get very concrete. So the first one we're going to choose, and it's kind of an initial example in the setting of signal processing or sound signals, is thinking of this square wave. So this square wave is a kind of basic fundamental concept in at least electronically produced sound. Okay? So example 3.4. Okay, the square wave is to emphasize its wavy aspect, you can draw these lines. These are supposed to be straight lines. So it's not a nice, elegant, continuous signal like the sine function or the cosine function. Square wave. It's alternately on and off. So it's off, then it's on, then it's off, then it's on. So it's a basic kind of discrete type oscillating signal. And if you run it with high frequency through a loudspeaker, you can set up a simple electronic circuit that will oscillate like this. Run it through a loudspeaker, produces a note. You run it at high frequency. The frequency range that humans can hear. It's typical frequency range that humans can hear. 20 to 20,000 hertz. If it's somewhere in that range, if you run that signal through a loudspeaker, it'll produce something you can hear. Outside of that frequency range, you won't be able to hear it. I might break the speaker. That's what speakers make. Okay. Specifically, we just focus in on one little portion of this, from minus pi to pi. So here's minus pi. Here's pi. Okay, so the specific function we're talking about is switched off and switched on. It's switched off between minus pi and 0, and then it's switched on. It doesn't particularly matter what value you give to f at 0 itself, whether it's switched off or switched on at the instant x equals 0 itself. Here I've said it's switched on at the instant x equals 0. That's not so important. The integrals will still be the same. If you changed it to have the value 1 at 0, it would still be the same. It would still be equivalent. So these heights here, this is the 0 level on the x-axis, this on the y-axis, that's the 1. Okay, so that's a picture of what our square wave is. It can be expressed as an infinite, as a Fourier series, as a doubly infinite or potentially doubly infinite combination of sine and cosine functions. We will obtain its Fourier series. So, i.e., what this means is we will obtain the parameters, obtain the coefficients a0, a1, all the other an's and all the bn's. The answer is given at the top of page 61, but we want to justify it. We want to work our way towards it. Remember, a0 isn't the constant term, it's twice the constant term. The constant term in the Fourier series is a half of a0. Now, if I asked you to, we can kind of look ahead and get a feeling for some of these values from the off. If I asked you to approximate that signal with the one single constant value, which value would you choose? If I put you on the spot and asked you which value, of all the values that you could choose, which value best approximates the signal? Ah, that's the best value, because half the time it's 0, half the time it's 1. I mean, you might argue some kind of argument for choosing 0 or 1, but maybe the fairest middle of the road value would be a half, just the average value that it takes. So we expect to see in the Fourier series expression, that's why it's a half. When you obliterate all the other information, just seek a single constant to represent the function, yeah, it should come out as a half. Half is the fairest choice. Okay? But let's see that that's what the coefficient does come out. So by definition, a0 is defined to be 1 over pi times the integral from minus pi to pi of f of x dx. So how do we integrate this function? F. We don't normally tackle integrals, functions presented like that case-wise, but how can I work this definition or work this integral? And the function is not that complicated, I hope you'd agree. Right? It only takes, some of the time it takes the value 0, the rest of the time it takes the value 1. It's not that complicated a function, so we really should be able to integrate. Remember, integration is just the area under the curve. There's the 0 level, so the area we're talking about really is just that area. That's a rectangle with pi, height 1, so it should be pi, yeah? The integral should be pi. But, you know, how you would justify it by the algebra would be, well, for every value of x between minus pi and 0, you're integrating 0, so you may as well forget about it. And the rest of the time, integrating from 0 to pi, you're integrating f of x, but you're integrating 1. So it's just the integral of the constant 1 dx. So this first half of the integral is clearly 0. And this first half, the second bit of the integral is clearly pi. Yeah, so it's just integrating the constant 1 between 0 and pi. So it's 1 over pi into 0 plus pi. So yeah, overall it comes out as a naught is equal to 1, but this a naught is halved, and that feeds in, that's the constant term in the Fourier series. I say 1 is expected. It's expected because we looked over the page, we saw half was the initial constant term for the Fourier series. That is the fairest value you would choose as a single value to approximate the Fourier series. You're only allowed to use a single value to approximate. Okay, we're kind of well, in some sense, a third of the way there. We've got the constant coefficient. So determining these other coefficients is normally done all in one go. So you determine all the ANs in one go, all the BNs in one go. Or at least you attempt to do that. Considering the integral, you may have to vary your approach to the integral depending on maybe the parity of n or different cases of n, but that's to discover. At least initially you set out to determine all the ANs in one go. So we'll consider AN for any value of n bigger than 1. So by definition, it's 1 over pi, the integral minus pi to pi, f of x times the cosine of nx dx. Okay, that's the coefficient formula from equation 3.8. There, page 60. Okay, so we're integrating the product of f of x with the cosine of nx. Okay. This becomes an exercise in integration. Hey, looks intimidating. We got to multiply f by this cosine. F is this funny function, but really f is, when it comes down to it, f is fairly simple. It's 0 for half of the time, and then it's 1 for the rest of the time. So again, that tells you split your integral up according to these cases. If you look at the equation on 3.8, page 60, that's, see, the AN is the coefficient of this basis function, cosine nx, in the Fourier series. Yep. So again, we should split our integral up as the integral from minus pi to 0 plus the integral from 0 to pi of whatever. Yeah. So we split the integral up. Just save myself the bother of writing that out twice again. But the integral on the first half is certainly 0 because f of x is 0 on that first half. It doesn't matter what values cosine of nx takes between minus pi and 0. We're only going to multiply it by 0. Just integrating 0. That's going to give us 1. We do get something potentially from the integral 0 to pi. So everywhere there, f of x is equal to 1 between 0 and pi. So we're just integrating cosine nx dx. So this looks very doable. Don't do anything with this, that's 0, and here we're just integrating cosine, so surely we can do that. So we get 1 over pi time, now the integral of cosine is sine nx over n, and evaluating that at 0 and pi. What comes of that? Does that amount to? Just for 0? Yeah, not much. It's just 0 because we've got to evaluate sine of nx at 0 or pi. But there, well, sine of 0 is 0. Sine of remember n is an integer. Sine of an integer multiple of pi is just 0 too. So it doesn't come to n. Always equal to 0. That's not bad. That's good. It simplifies the Fourier series. It means there will be no cosine functions in the Fourier series at all. That's as expected as well. So when you glance at the answers given, you don't see any cosine functions. Okay. So that's as expected too. Yeah, you can kind of give a motivation or an intuition about why that might have been true. When you looked at the signal, you see the one thing that all those cosine functions have, the one feature property that all those different cosine functions have, is they're all symmetric around the y-axis. The x equals 0 y-axis. The cosine functions are all exactly symmetric under reflection in the axis. Okay? But the square wave function we're looking at is exactly, it's often called anti-symmetric. Symmetric function is one, when you look at a positive argument and the same negative argument, it takes the same value. That would be symmetric function under reflection in the y-axis. But when you look at a function, so here at this point here, this is taking the value 1. This is its reflected point here, it's taking the value 0. And when a point takes the value 1, it's on the negative side, its reflection is taking the value 0. So it's exactly not symmetric at all in terms of the values it's taking. Okay? When it's taking the value 1, its reflected argument is taking the value 0. So it's very unsymmetric in that sense. So that kind of shows you why there are no cosine functions contributing to it, because the cosine functions are all symmetric. This signal has nothing, I mean, it does have some symmetries, we can see, but it's not, it doesn't have any symmetry under reflection in the y-axis, under plane reflection in the y-axis. And if we included any of those cosine contributions to the Fourier series, they would contribute symmetric behavior to it. But it's not symmetric. That's kind of like a post hoc or a hand-wavy justification for why the ANs are 0. But it comes out formally through the integral. So now the BNs. Finally, the BNs for, well, we'll attempt to do it in one go, just like we did with the ANs. Any questions before I continue? Any clarification needed? We're 2/3 of the way towards determining the Fourier series. All we've generated, well, we've generated the fact that constant terms are half, and the AN coefficients are all 0. There are no cosine functions. So we attempt to get the Bn. Well, by definition, it's 1 over pi, integral minus pi to pi of f of x with sine nx dx. And you break down the integral in exactly the same way, because f is switched off in the first half of the integral. So really, it's just the second half of the integral. Integral from 0 to pi sine nx. Okay. As f of x equals 0 and 1. 0 on the minus pi to 0, and 1 on the 0 to pi. So just from the definition of f. Okay, we got to integrate sine nx. That's not too hard. It integrates to minus cosine nx over n. 0 and 1. Very doable. Now, what does this come out as? Well, it comes out as minus the cosine of, well, this n I can slip out here, so it's 1 over n pi, minus the cosine of n pi, whatever that is, minus, so it's minus, so it's plus the cosine of 0, n times 0, which is just 0. Well, that is at least anyway minus the cosine of n pi, whatever that is, plus 1. Cosine of 0 is 1. Now, what is the cosine of n pi? Cosine of n pi is, oh, I saw you waving your finger. You must be halfway there. What's your finger doing when you pass through n pi?
Yeah.
Always at the bottom?
It's always. No, it's plus. Oh, yeah.
Plus, so it's your finger, if you're doing the cosine function, your finger is either at the top of the wave or at the bottom of the wave. Right? So it's either plus or minus 1. So it's 1 at 0, it's minus 1 at pi, plus 1 at 2 pi, and there'll be minus 1 again at 3 pi. The cosine of n pi is plus 1 or minus 1, and they alternate. So it's down to whether n is odd or even. So this quantity here is either it's either 2 or 0 in this bracket here. So it's just down to whether n is even or n is odd. Well, when n is even, you get a plus 1. So 0 pi, 2 pi, 4 pi. When n is 0, you get a plus 1 out of the cosine, so it's minus 1 plus 1, so it's 0. So it's 0 when n is even. When n is odd, the cosine of n pi is minus 1, but it's minus 1, so it's 2. So it's 2 over n pi. This is what I meant by sometimes you got to split. You know, you try and get the bn's all as one quantity, one formula of n. Sometimes it doesn't work out. There might be different cases. I mean, this is still a formula of n. It's just a case-wise expression. So we determined all of the bn's. Half of them are 0, half of them aren't. Okay. So we can present the Fourier series. F of x, the square wave function, zero on minus pi to 0, 1 on 0 to pi. We can present it. We can have a look at it. It's half of a naught plus the sum of all the an's cosine nx plus the sum of all the bn's sine nx. N going from 1 to infinity in both cases. A naught we had as 1, so that's a half. The an's were all of them 0, so they don't feature. So we just get the bn's. So we're summing from every value of n from 1 to infinity, but we're only going to do it when n is odd. So n odd. And in that case, you get 2 over n pi, but the 2 over pi we could slip to the front. And then we have 1 over n sine of nx. Everybody appreciate how we're handling our summation index here? We're summing from every n from 1 to infinity, but we've added a condition. Only those n which are odd. So we skip n equals 2, 4, 6, and so on. Yeah, only the odd n. Now, in general, we only like to supply extra conditions onto indices like that when they're really required. If there's a sweeter way we can do it, we often like to do that. So, and here I'll switch to an m, just to emphasize that I am switching behavior. If you just want to go over all the odd n's, so I can run through all the odd n's by running through all the integers n, but just looking at 1 over 2m minus 1. That do it? So when m is 1, this generates 1. When m is 2, this generates 3. When m is 3, no, when m is 2, this generates 3. When m is 3, this generates 5, and so on. So that generates all the odd integers as m runs through all the integers. And that's sine of 2m minus 1. So that should be exactly what's written over the page, except to use n for the summation index, but who cares? So it's a half plus 2 over pi. Sine of x is when m is 1, plus a third sine of 3x when m is when m is 2, plus a fifth sine of 5x, etc. When m is 3. Okay, so it's this combination of sine functions, all sine of all the odd multiples of n, divided by the reciprocal of that on an integer, the whole thing rescaled by 2 over pi, shifted upwards by a half, that generates the square wave function. Remember in the initial lecture on Fourier series last week, I showed you a Sage interactive device where we looked at the square wave function and its increasing order Fourier series approximations. It was these functions, that the thing was displaying. So up to order 5, it's this combination of sine functions and constant that you see there. And as you include more and more terms in, you get a tighter, you always have this oscillating sine Fourier series, this combination of sine functions. As you increase the number of terms, the oscillations get tighter and tighter and tighter around the square wave function. It better approximates the square wave function. Remember, this equality here, let's put, maybe not quotes, but maybe there's an asterisk, a footnote needed on the equality. The equality holds at every point of continuity. Right? There's one point of discontinuity, which is x equals 0. And at that point, the infinite Fourier series is going to return the fair value, the average of the two-sided limits. It's going to return the value of half. You can definitely see that, because what value does this thing give you when x is equal to 0? Well, you just substitute x equals 0. When you substitute x equals 0 here, you have sine of 0 to 0. So that whole thing is just wiped out. You just get the value of half. So that's as expected, as declared by the Fourier's theorem as well. I haven't seen the movie yet, but I've seen the posters for the Showman movie. What's his name? Hugh Jackman? I'm like Hugh Jackman with the hat. Prepare yourselves. And some magic, right? Something astounding that comes out of this, right? We're going to evaluate the Fourier series at a nicely chosen evaluate this at a nicely chosen x. Now, what nice value of x could there be? I mean, 0 is kind of nice because all the signs are 0, so you get the statement that a half is equal to the average of 0 and 1. That's not that astounding. You knew that anyway. Other nice values of x would be ones that also simplify the sine functions. And what other way could we simplify these sine, or look at nice values that they have? Well, it's like with your finger you were doing that. The top and bottom of the sine wave are nice. The top and bottom of the sine wave are +1 and -1. So if we could arrange it that we got +1 and -1 out of these sines, that'd be nice. So we can do that by evaluating at sine of pi over 2. At x equals pi over 2. So here's the sine function. It's like this. There's the sine function. There's pi over 2. Sine of pi over 2 is +1. 2 times pi over 2 is pi, which is 0. But there's 3 pi over 2. It's -1. Here's 5 pi over 2. Back to +1. Here's the next one, 7 pi over 2. Back to -1 and so on. Now what's f of pi over 2? F of pi over 2 is 1. F of pi over 2 is 1. That's the left-hand side of the Fourier series. Let's go to the right-hand side. The right-hand side, you got a constant half plus 2 over pi times, okay, sine of pi over 2 is +1. Sine of 3 pi over 2 is -1, so it's -1/3. Sine of 5 pi over 2 is +1 again, so it's +1/5. So these sine terms are going to alternate, and they're each of them scaled by the reciprocal of that odd integer. And that continues for infinity. So we have 1 equal to 1/2 plus 2 over pi. Now what is this? What's going on here? We're summing over every value of m from 1 to infinity. We're generating the reciprocal of the odd integers, so 2m minus 1. But with alternating sign. Positive on, we're starting at m equals 1. The positive on the odd m's and negative on the even m's. So we do -1 to, we want the positive on the odds and negative on the even. So you got to add or subtract 1 from m. Just your choice whether you prefer positive or negative things. Of course, we should prefer positive things. So -1 to the power m plus 1. That gives us a plus sign when m equals 1. So it gives +1 over 1, it gives us that. That's just a nice way of writing the infinites, the alternating series of the reciprocals of the odd integers. What we got here. Well, you see, also lurking, okay, so what, you say, but also lurking in here, we've got pi. So you bring the half over the other side, you'll have a half over here, but then clear the 2 over pi, multiply by both sides. So it's telling us that pi over 4 is equal to this sum. Or if you like, that pi is 4 times that sum. So this sum is the alternating series of the reciprocals of the odd primes. And that's fairly, like, you know, when I first encountered this, I was confused and, you know, wondered what life was all about. Because, like, how was pi originally defined to you? How did you first encounter pi? To do with circles, isn't it? All circles are equivalent to one another. You just zoom in or zoom out on it. There's this fundamental relationship in the circle, the ratio of the circumference to the diameter. Right? The ancient Greeks appreciated this, that this ratio was the same for any size of circle. Fundamentally, circles are all the same. So pi is the name given to this ratio, and over the years, we've got tighter and tighter approximations of it, 3.14, yada, 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 something, right? But it's also 4 times the sum of this infinite series. And what was initially confusing and mystifying to me, and still is really, is like, it's not obvious where the circle is here. If pi is to do with circles, then surely in any equation for pi, you see circular stuff. It's not amazingly obvious or intuitive when you look at it like this, where the circles are. Because we've got the alternating series of reciprocals at the odd prime numbers. So it's an intriguing formula for pi. Okay, so intriguing? Probably. Yeah. An intriguing formula for pi. Now you could use this. Okay, remember, think of the problems the ancients had of finding out what pi was. At first, they actually drew big circles with pencils and string, or scratched them in the sand. You pin one end of a string in the ground or a bar, you let the other be free, and you can describe a circle. You can draw a big circle, measure the circumference, measure the diameter, calculate the ratio, you get an approximation for pi. But pretty soon, your things are so big that they're breaking down, they're losing accuracy, and fundamentally, you can only measure things so accurately in reality anyway, especially the ancients. And you can measure things pretty good. So how do you get beyond the limitation of physical measurement to get further and further accuracy on pi? Well, one of the things you could do is use this infinite series, because this stuff is all available to a computer. Because what are you doing? Well, you're adding stuff together, you're starting with integers, you're working out reciprocals of integers. Computer can certainly work out can get decimal approximate. Well, they can work out the exact values of each of these decimal expansions. They're either infinite recurring decimals, like a third, and they're all rational. So they're either recurring infinite decimals, or they're finite, ending decimals expansions. So you could program a computer to evaluate any particular finite part of this right-hand side. So you can calculate better and better approximations to pi, just using basic arithmetic operations. And when we use computers to calculate pi, so we've calculated millions and millions of digits of pi, humans have. Now, they're not using this formula. This formula, while it does converge to pi, amongst all the formulae for pi we know about, it converges very slowly. So we know about much more faster converging series expansions of pi. So when people apply supercomputers to calculate loads of digits of pi, they're using much better, much faster approximating series. But the principle is displayed here. Okay, we can program binary circuits to evaluate these things on the right-hand side, and evaluate longer and longer versions of them. You're getting better and better approximations to the value of pi. And it falls out of it's nicely illustrated in all these Fouriers. They're nice consequences we can get at. Okay, so as another exercise, the next function you should tackle, I think it's one of the exercises. If it's not, I'm going to specify it to you now.
We've only got 4 minutes left,
Yeah, I know. Well, it's in exercises 3.2, but so the next thing you should do is you should obtain a Fourier series for the identity function. i.e. the function f of x equals x. So not the square wave function. So this is the function of minus pi to pi. It's the value x. It's a straight line graph. So you can calculate its Fourier series as well. You can go through it the same way as we did the square wave. Okay. So exercise 3.1 is opened up to you now. And okay, there's a whole other section of odd and even functions before exercise 3.2, but you could look ahead. Look ahead to 3.2. You could tackle some elements of it. But certainly this exercise and exercise 3.1 would be useful. And if you do this one, then try g of x equals x squared. We'll look at some of the powers of x. You're getting infinite expansions of these functions in cosine and sine. Okay, we'll finish there for this evening. Thanks for your attention.